So Arf, which translates to Happy Halloween from Sky. She wore her wolf in sheep's clothing outfit last night, and we got very few trick-or-treaters than we normally get, which was interesting. I guess maybe Sunday night, pandemic, I don't know. Maybe the neighborhood's growing up. So today we might finish chapter 5, we'll see. And then if we do, it's chapter 6 next, it's the SN2 reaction. So I have the easy extra credit assignment posted for you on Canvas. About 10 of you maybe have responded to it already. And all you have to do is let me know where you plan to transfer, because I want to help you make the best decision on about taking Chem 12A and 12B here at Sierra. So if you're transferring to UC Davis or another UC, then both Chem 12A and 12B here at Sierra will transfer over to those colleges, and you'll be done with sophomore level O.Chem. And you won't take any more O.Chem unless maybe you're like a chemistry major, maybe biochem, and you just decided for an elective to take like an advanced organic chem class. But if you're a biology major, then I think you're done with O.Chem at that point. But if you're transferring to Sac State, here, that's an interesting situation when students are transferred to Sac State. Here are the course numbers and descriptions. So I won't go through each of them now, but you can see like the first couple here are just like not really for you. They're more for like geology majors, people who aren't in the biology chemistry type majors. But the other ones we got like Chem 24, which is like our 12A. And then strangely, our 12B is 124. I guess that's not too strange, huh? But then they have a 124 for a lecture, but then they have a 125 for a lab, 25 for a lab. Yeah. I guess that makes sense. Yeah, the 24s are lectures, 25s are labs. That's it. Okay, but let me explain what I mean here. Okay, so pros and cons of taking Chem 12B at Sierra College versus skipping it and waiting till you get to Sac State. So the way it works out, here at Sierra College, you have Chem 12A and 12B, first and second semester. They're sophomore level courses, same as like at the UCs. And then you wouldn't have a third semester, which would be a junior level course. Those who transfer to Sac State, their Chem 24 counts as our 12A lecture. And they don't have lab their first semester. If you took all your O.Chem at Sac State, they have you take lecture with no lab first. And then they have you take your second lecture with your first lab. And then they have you take your second lecture all by itself. And because they're doing it over 3 semesters, they consider this an upper division class, a junior level course. So there's nothing at Sierra College that can transfer and take the place of a junior level course. We're only freshman, sophomore year college. So what my students have done in the past is if they've taken 12A and 12B here, then they've counted, they're done with the lectures, first and second lecture at Sac State and the first lab, but they still have to take the second lab. It's just a strange thing that happens there. But of the students who've done it, I've heard back from a number of them, and they say it's pretty easy. It's like similar stuff that we've already done, but it is another class you have to take. So, yeah. So if you take 12A and 12B here, oh, let's look at the benefits. I'll just do this. Benefits of taking 12B at Sierra. Same instructor each semester, so you'd have me next semester, and you could take it in 2 consecutive semesters. So I noticed early on that after Christmas break, we do 12A Christmas breaks like 5 to 6 weeks, and then 12B. That beginning of 12B, the first couple weeks, I do kind of 2 things at once. I do new material, of course, because we're learning new material, but also reviewing the 12A material because there's like a lot of rust over that 5 weeks. It seems like students come in and they're like, wait, what happened? What did we learn last year? So I do like memorization quizzes again for like spectroscopy, PKAs and stuff. And I give a big workshop to get us reviewing the old reactions and things we learned. And then after that first couple of weeks, then the review, they're like, good, we got 12A down again. So if you don't take the course in consecutive semesters, it's much tougher. And so I think, well, I'll get to that. So if you say you took like just 12A this semester and you didn't take 12B here, but you waited till next fall when you transferred to Sac State, it's going to be tough because you'll have the spring semester with no O.Chem, then all of summer with no O.Chem. And you got the Christmas break too, no O.Chem. Christmas break, spring semester, summer, and then you're back to O.Chem, and it's been a long break. So that could be tough. And then topics are not, what happened? Topics are not repeated or omitted if you take 12B at Sierra. So if you take it from me both semesters, then I'm going to be like continuing on where we finished off at 12A. Whereas if you take the second semester somewhere else, they might have not done topics we already did this semester. And they most likely did topics we didn't do. And they're expecting that you would know those. So you'd have to like kind of catch up on that. So, but then the benefits of not taking 12B at Sierra are that you end up having to take 2 O.Chem labs total. So if you took 12A here, you get 1 lab, and then when you switch over there, you wind up at this point. You got their second lecture, their second lab, and then their third lab. So oh, you know what? Oh, wait, let me see. No, I think, yeah, if you transfer after the first semester, I'm pretty sure our 12A lab is to make it means you don't have to take this Chem 25 lab. I'm almost positive. I actually I emailed the counselor at Sac State. So I just wanted to let you know this. If you were me, I would say finish it at Sierra, get it done. But I don't know what all your schedule looks like. And it seems like in the past, I had like usually, I don't know, maybe I'm wrong on this, but I thought I only had like 1 or 0 students transferring to Sac State. And so the ones that did would just wind up taking this extra lab there. And they said they liked it. It was pretty easy because I think they learned how to use the NMR there and things like that, which you've already done a lot of, you know. All right, and then so a little bit more. Here's the catalog description of that extra course that you'd have to take if you did 12A and 12B here. Here's the extra lab. It says Advanced Organic Chem Laboratory. It doesn't say junior level anywhere, but I'm pretty sure it's considered junior level. None of their courses have whether they're sophomore or junior level, which I think is interesting. I don't know if the 125 versus 25 means something. I don't know. And then it focuses on advanced laboratory techniques. Not, and this is interesting, not intended for pre-health professional majors. So that's most of you, I think. Your biology majors and wanting to go into health fields like doctors or pharmacists and stuff. So I'm kind of confused by it. I don't know. Everything's up to you, but I'd take 12B here. Okay, exam 2 average, 75% was the average. It got better. I think we were 69% on exam 1, so I'm glad that went up. But I still want it higher. I want it to be 80% average. I want it higher. The high was 98%. There was 2 people with 98%. Good job. And there was 12 scores in the 90% plus range. That's out of about, I think it was 37 tests taken. That's really good, 12 out of 37. And exam 2 corrections are due today and tomorrow in lab. Remember to correct them all perfectly, use the key, and anything you missed, or even if you didn't lose points, if I made a comment, fix it, write out the answer perfectly according to the key. It's disappointing when I'm grading these and I see like someone like half answered it or like just answered it wrong again. It's like, well, what's going on? You have the key. So take some time on that. And then always write sentences saying like, oh, I missed this one because I was confused. I thought it was a late transition state, blah, 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 something like that. And then after exam 2 quiz today and tomorrow in lab. So come ready for that. I mean, study the key and remember to study the ones you got right too. A lot of times students will miss the question they actually got 100% of the points on in the exam. And then now they're rusty on it for some reason, but don't do that. I got a question about do you write your corrections on the exam or on separate pieces of paper? Either way is fine, but maybe on a separate piece of paper might be more clear and easy for you to make sure you do all of it, because sometimes people, they just write a couple trick and scratch things on the exam. It doesn't help them. All right, and then we may finish chapter 5 today. We'll see. I don't know if I actually will. I probably won't, but if I do, I'll set the due date for the homework. But either way, start working on the homework. Homework D, chapter 5 homework, because you'll need to start turning it in. You know, it's not something you should wait till we finish the lecture material on. You should start it as we go. And finish the wet chemistry of the crystallization lab today and tomorrow. I've gotten a lot of those turned in already, but I know some of you need to do like one more crystallization or something. So do that today and tomorrow in lab. Get that done. And I'll give you more time in lab today. We will have the quiz, but I won't have a lot more to take up the beginning of the lab period. And get the report to me by this week, and I won't count it late. I think it's listed as being due on the 29th, but I won't. I'll extend that date a little bit. I think I already did. I think I went in there and changed it. And I'm nearly done with crystallization. I mean, the next lab, chromatography. But you can start reading about it already. So start reading that. Read up to the point of wet chem by this Wednesday or Thursday. This way, if you get done with extractions this Wednesday or Thursday, you can start right in on that without having to read the intro in lab. And I'm going to stop filling in the due dates sheet. I think I have too many places to put due dates in, and I mix them up. And so I figure, okay, you guys got the, you know how it works now. So I'll have the same late policy, and you'll just need to calculate on your own instead of looking at the due date sheet. So if it's 4 days or less late, no points taken. 5 to 7 days late, 50%. So just try to get things in try to get things in on the due date. That's the best thing. And then if you're going to be late, have it under 4 days. So I had a question about the chromatography lab pre-lab. So the pre-lab will be read up to the wet chem and answer the questions that lead up to that. I think there's a few. Let me finish this off and then I'll actually look. 8 days or more late, then it's minus 100%. Okay, and let me pause on that. We're on 12. Let's look at this chromatography. I'm right here. What page am I on? I am on 42. It's not going to be, this one will be shorter than the other ones a little bit. So let's see. Yeah, we got the TLC. Yeah, we got questions. Yeah, you watch a little bit. Yeah. Yeah, I guess I did keep that in, didn't I? Yep. So it's up to page 19. And there's a video to watch. So up through question 15. Right, you're welcome. Okay, so as always, you can come to lab early. Today you come at 1:50. And clean up before the beginning of their lab so that they can start their quiz after exam quiz without goggles or anything. And no Shavember starts now. If you shave today, it's okay if you forgot. Just stop till December and you can get the easy extra credit points for cancer awareness. All genders take part. Do nothing and get +1 points. Don't shave all of November and let me know after and you get 1 point extra credit. No need for proof. I'll trust you. And Stereochem workshop is due this Wednesday, Thursday. So hopefully you've made some good progress on that already. It's not too long of a workshop. And try to get all of those answers 100% correct. So ask me for help or classmates. It's not something like an exam where you have to just show me what you know. It's a workshop where you're trying to get the skills down. So let's get it all right. And then honor students, I'll give you an assignment this week. It'll be like I think it'll be an SN1, E1, or E2 reaction. Google slide animation. So remind me about that. We'll get going. I wanted to finish that exam week before I did that next assignment for you. And then don't forget to do this great extra credit assignment. I've got a couple of these. This is a nice one. It really makes you think about the symmetry of molecules, and that helps you in spectroscopy, but also with reactions and everything. And if you're not doing as well as you'd like in the course, like if this exam 2 wasn't good enough for you, you're like, oh, I want to be on those 90% scores, then start coming to my office hours, Tuesdays, Thursdays, 9 to 10. I remember when I was taking physical chemistry, that was a tough one for me. That's a tough one, I think, for everybody. I just decided to make my Professor Olmsted's office hour my new class. I said, okay, Professor Olmsted, I'm coming every office hour. And he's like, okay, come on by. And then so I'd be there every time and just show up, and I'd have questions for him. But if I didn't have questions, I go, can you make me a question? And he's like, sure. So it helped me get through. I wanted to make sure I got an A in physical chem, and I did. So that was nice, even though I felt like I understood about 3/4 of it. And treat the time, my office hour time, like as a new class you just added into, so you have to go every time. And you can come in person in my office here, or we can be in the lab too. We got the big whiteboard, or you can come on Zoom from wherever you like. Wherever you can access Zoom, and come with questions or not. I'll make up problems for you. So that's how I start the office hour. Those of you who come know, I just say any questions, and then when people have questions, I'll go through them. Like they say, oh, can you help me with this question 12 on the homework, whatever. I'll do that for them. But then after, usually I have no questions, but if I do have a question, I do that first. And then after that, I'll just start making up questions for them. So, and then when I make up the questions and they're working on them, if they have a problem, I can tell right where they're stuck. So I can back it up and make sure they get that concept so they can now do the problem. And it really helps. I have a question. What do you do in physical chem if you can be? Oh, physical chem's like general chem on steroids. And they go into like, you know, you have the ideal gas laws, PV equals nRT. Now they're like, oh, that was a really simplified version of it. And they just go crazy. And yeah. And then if you are behind on the lectures, like, oh, I haven't watched that last lecture. I feel embarrassed. I shouldn't come to office hours. Still come. Don't worry about it. I'm not here to discourage you from coming. I want you to come, even if you feel like, oh, I have no idea what's going on. Then you should more likely come. It shouldn't be a thing to stop you from coming. And an hour studying with me can be like 4 hours studying alone, I think, sometimes, because I can find that little thing that's holding you back and fix it right away. All right, so okay, that was my answer. So Annalise had a question about one of the stereochem problems, which, let me see which one it is, Annalise. Maybe I'll do it now, but we'll see what it is first. Which question number were you thinking? Number 4, chair conformations. Okay, let me look. I think I can. I'll just kind of briefly go over it real quick for you to help you out with it. Get you going. Let me see. Oh, I think I know what you're talking about. All right. So for this one, I'm guessing you already figured out that there's 3 different. Is this? Oh, this is bromo. I don't know why I'm going ethyl on this. 3 different chairs here. Not chairs. 3 different molecules for this. 3 different stereoisomers. The wedge, which is the same as the dash. This one is meso, huh? And then the dash wedge. These ones are different. Because if I get my stereochem right, A, B, C, this is R, this is S, so this is S, this is R, this is S, this is R. So you can see those 2 are different. They're enantiomers, huh? All right, now you're asking about the chair conformation, and I believe, let's see, I think you're asking about the meso one, huh? So let me,
The way I did that one, I crossed out the miso one and said that the dashed back one, does it matter which one you cross off
the
for being?
dashed one and the wedged one are the exact same molecule. So no, it doesn't matter.
Doesn't matter which one.
No. If you pancake flip it, right, it goes dash dash. So the way I'm viewing this bromine should be equatorial up here, and then at 5 it needs to be, oh wait, this one's the obvious one, huh? You probably had no problems with this. Is it the other ones you're having issues with?
I drew my bromines on the other side, so I did 1 on the bottom left and then 3 on the top.
What did I
This
do?
place.
This is 1, 3. I drew these wrong, huh? I drew the second one wrong, didn't I? So did you have any problems figuring out the higher and lower energy chair of the miso?
I just kept getting like one bromine was equatorial and one was axial, and it was the same on the other side. They just flipped.
Yeah, so what winds up is they're the exact same energy.
Oh, okay.
So you probably just like haven't seen that, huh? And two that are exact same energy.
Yeah, I think that was it. I wasn't sure
That
what to do
threw
with
you
that.
off a little bit, huh? But this one's pretty obvious which one's the lower energy, right? Which one's lower energy here? These are not the same energy.
The left is lower.
Yep, the diaquatorial, huh? All right, and then this one, I'll just do this one really quick too. Let's do it. It's kind of ugly, but whatever. Let's get it done. So we're gonna go, I'll go the same numbers, 1, 2, 3. I kind of tilted this one, huh? Whatever. I'm trying to do this fast. I don't know why I moved it around. I'm probably gonna confuse people. Let me not do that. I'll just put my 1 here, 1, 2. Hope this isn't confusing anybody. So 3, if I go 1, 2, 3, this would be 3. It's going to be bromine down. 4, 5, bromine up. And then that's 1, 2, 3, bromine down. Bromine up. Yep, so they're same energy. Okay, good question. And then now, quick review. Let's compare these different isomers. So constitutional, oh, I gotta switch my thing here. I'm not sure what you mean by I got 3, but I'm hoping you figure it out. I hope it makes sense now, and you could do the last stereoisomers chairs, and they'll also be the same energy. Okay. So a quick review, constitutional isomers, they have the same molecular formula, different connectivity. So something like this guy is a constitutional isomer because they're both 1, 2, 3, 4, 5. C5H10 plus 2, 12. 1, 2, 3, 4, 5. C5H12, but they're connected together differently. And then enantiomers, if I have one like this, I can quickly draw its enantiomer just like by switching any 2 groups. I'll switch the bromine and its hydrogen. Now those are enantiomers. They'll have opposite signs. Here, actually, let me do this too. I'll make it a little more complicated one. Let's go wedge. No, now I'm making a miso. Dash. Wedge. Okay, so these are enantiomers because we've got A, B, C. This is R, A, B, C. This is R, right? Yes, S, S. So they have the same molecular formula, same connectivity, different in 3-dimensional space. their relation to their mirror images, they're non-superimposable. And their absolute configurations, they're all opposites, huh? See how that applied here? It went from S to RR. And their physical properties are the same. So let's say that the melting point of this one is 102 to 103 degrees Celsius. What's the melting point of this one then? It'll be exactly the same. Bingo bango. What about if this one has got a rotation of minus 25 degrees, an optical rotation? So it's rotating plane polarized light counterclockwise by 25. What's the rotation of its enantiomer? Plus 25 degrees. Yeah, same magnitude. And they're both chiral because they rotate plane polarized light. And their magnitude's opposite. Okay, cool. Next up, diastereomers. They're not quite as alike as a they're not quite as alike as enantiomers. They're a bit more different. So let's say, for example, I've got this chlorine dashed here, this fluorine dashed here, but I still have the alcohol dashed. Let's calculate R and S of these guys. So the chlorine one is R. This one's going to go fluorine's A. Fluorine's going to win B, C. This is R as well. So I know S, S. And the alcohol, it's A, B, C. It's R as well. And it stays R. Okay. So let's see if this works. So do they have this on my table here? These diastereomers, do they have the same molecular formula? Yes. Same connectivity. But different in three-dimensional arrangement. Relation to the mirror images. Are these mirror images? If I try to make them mirror images, no. If I like flip them around and spin them, the alcohol will be wrong. They're not mirror images. And then some of the absolute configurations are the same, some are different. So like the R is to S, so good. It's looking like an enantiomer, R to S, but then O, R, R, they're the same. So diastereomers. And then physical properties. If this one's melting point is like 115 to 117 degrees Celsius, what's this guy's melting point? I don't know. Close. Close, but not the same. And then physical properties. Optical activity. If this one rotates plane polarized light like minus 11 degrees, what's this one do? It might be minus 2 degrees. They're not related. You can't predict it. Okay. And then meso compounds, that's a tricky one. So meso compounds, they're achiral members of a set of chiral isomers. So for example, this one's meso. Let me go. Boom, boom, boom. So this is a meso. So actually, let me move this guy over a little bit. I got some questions here. Let me see. Okay, so I've got these two here. This one, the stereo center on the left carbon with the bromine is ABC. This is R, yep. And then this one is S. Okay, so let's see, is this guy meso? Is it achiral? It is achiral. It has 0 degrees rotation. And I think, do I mention the plane of symmetry in this table? I don't think I do, huh? But I do mention the number of R's have to equal the number of S's because, yeah, I got one R and one S. So it's like two enantiomers are attached to each other through this point here. And if I rotate the bond on this thing, you can see the other bromine becomes wedged as well. So you can see a plane of symmetry through this molecule right down the middle. So it's as if I have a perfectly equal mixture of two enantiomers. So like whatever this stereocenter rotates plane polarized light a certain degree clockwise, say, and this one will go counterclockwise the same degree. So they'll just cancel each other out. It's like a perfect racemic mixture. And it needs to be a meso. It also needs a stereoisomer that is chiral. So if these guys are stereoisomers to it, they're related as diastereomers, and they're both chiral, so it's meso. All right, and then the racemic mixture is a 50-50 mixture of enantiomers. So if I had like a 50-50 mixture of these two, then they would cancel each other out. They'd be achiral, not active, because the plus 25 would be canceled out by the minus 25. And the weird one about racemic mixtures is their melting points will be different. So if I have this enantiomer all by itself, it could have this melting point. Then this enantiomer all by itself, exact same melting point range. But when I have a racemic mixture of both, it could be a little different. Like it could be 100 to 101 or something, because they can like interact differently because of their stereochem, like puzzle pieces. They fit a little different together than apart than individually. Okay, so enough review of that. Let's get back into this chapter. Did I leave the outcomes? I think I did. So I'm going to skip over this outcome right here for now, because I think I'll be doing that in lab next semester with you. So this red one, skip for now. I'm saying that on November 1st, 2021. Okay. But even though I'm going to skip it, I will say this really quickly. When I've been giving you values for enantiomers and diastereomers and saying, oh, their optical rotations like plus 25, minus 25 degrees, this is the calculation to get that. So this is this specific rotation is what I've been giving you. We'll talk more about it later. It has to do with the observed rotation, how much the plane polarized light is rotated. And then you also relate to concentration because that affects it, and the length of the tube you have in the polarimeter. Okay, so we went through the mesos. Oh, and then also this here too. I should put those all together, huh? Yeah, sorry. Outcome 12. Let's make it 13, 14. I'll make this the new 13, 14. Okay, so we defined meso already, and we got our table we did already. Okay, let's do a racimization. Yeah, let's do it. And then it's into fissures. Cool. All right, so racimization. Sometimes you can have a molecule that's chiral, and then it can be made into a racemic mixture. So we say it's been made into a racemic mixture. It's been racimized, racimization. I'll show you a common example of that. When you have I don't know why my Jamboard's got like a question mark on this guy. Whatever. When you have a carbonyl containing molecule that has an alpha stereocenter, this guy can be racemized. So let's say I just have a methyl here, right? So I have a stereocenter there. Can anyone tell me, does this look like R or S? This stereocenter right here. I had a question about, will meso compounds make more sense? They will. Yeah, and you mainly look for a plane of symmetry through the molecule. Yeah. All right, and now for this one, I got to guess at the stereocenter being R. Let me look myself. It's going to be this carbon first because the oxygen. That's second. This is third. D is back, so A, B, C. Looks clockwise to me. So this stereocenter is R. If this molecule is exposed, let's say we have, well, let me say this initially. Say we have 100% just this molecule. If you expose it to acidic water and give it a little bit of time, it can become a racemic mixture in which you have like 50% R and 50% S. Which is, this is then defined as a racemic mixture. And let me state that this is R, so then that's obviously S, right? Yeah. All right. So initially we might have said this molecule here is chiral and it's got maybe a minus 31 degree rotation. So in the product side, we have a minus 31 degree rotation here and then a plus 31 because they're enantiomers. But together, a chiral solution. So we started off with a chiral molecule. It was rotating plane polarized light when it was all by itself. It got exposed to some acid and water for a little while, and it became a racemic mixture of both the minus 31 and the plus 31. Since there's equal amounts of them, the plane polarized light goes minus 31, plus 31, minus, it comes out 0. This can be a problem for chemists because they may want just this R enantiomer and now shoot a little bit of acid and water around, and now I've got the racemic mixture. I got the S I don't want. So if you're an organic chemist and someone asks you to make a molecule with a stereocenter on the alpha carbon, this is alpha to the carbonyl, you should like cringe. Oh, really? Because it can racemize on you. If it doesn't matter whether it's R or S, then you don't care. But if you need just one enantiomer there, it's hard to keep it. Okay, so what's the mechanism? How's this happening? Over here, let me actually state that too. So alpha stereocenters to easily racemized. How does that happen? The mechanism is pretty straightforward, actually. I'll show you down here. So we're going to start learning more and more mechanisms, and there's a lot of like trends we'll learn. One of them is if you're under acidic conditions, like this reaction, normally the first thing to happen is protonation. So what's going to happen initially here is the carbonyl oxygen can be protonated like this. And I'll like a lot of times give these letters. So this P for protonation in this first step. Okay. This can also happen on the other side. I don't know if I want to go so complicated. Yeah, I'll do it. I'll do it. Okay, here we go. Let's go correct. This is actually a different molecule than the one above it. So it can be protonated on this side of the carbonyl oxygen or that side. So and you'll get, I think you'll get equal mixable. It won't really matter in the long run of this mechanism, you'll see. Okay, now after this first step, there's a hydrogen right here that's going to come off. Like this. And then imagine a roach hinge right here. Remember those hinges where it's like the electrons swing over that hinge? It's going to go there. And then this pi bond is going to go up here to the, you can see like kind of the driving force of this is to get rid of that plus charge on the oxygen. And what you end up with is the following. Okay, so this is called an enol. We went from a ketone to an enol. The reason why it's called, does anybody have a guess at why it's called an enol? What does en sound like? Yeah, en is for the alkene part, and then all for the alcohol. Enol. All right, and now what happens is the next step racemizes. So this lone pair can drop back down. We have a roach hinge here again. And it reaches out and takes the hydrogen back. So it's basically a reverse of the step we just did. But when it reverses, this hydronium can come from our side of the screen to make the hydrogen wedged, or it can come from behind to make the hydrogen dashed. It's got an equal opportunity to attack either side of that. So the product of this mechanism is going to be the racemic mixture. Well, almost. It's almost done. It's not quite done yet. Huh? So I'll have 50% with the hydrogens where it started, plus 50% where the hydrogen's wedged out now. So let me make sure you understand that concept. Hydronium. Protonate. Can't see my typing. Hydronium can protonate from either side of the enol equally. What it comes down to is steric hindrance. There's the same steric hindrance on either side of the enol, coming from our side or from the back side, because the molecule is trigonal planar all through here, huh? And then, yeah. All right, so we're almost done. Hopefully you could see the final step of the mechanism is pretty straightforward. It's just a water molecule deprotonating it. Need to give myself some more room. Think I can do this? Let's see. Yes, I can. All right. This mechanism, we're going to go over it later more. So you don't have to memorize it right now. I just wanted to give you an example of what I meant by this tautomerization, like how it can happen. So this is the one that'll give you the dashed if I do the mechanism on that one. And then the other one will also get deprotonated. And does anybody notice how the hydronium, we started with one hydronium here. Got a hydronium. It was used up to become a water molecule. And then it became a hydronium again. And then it became water again. And then it became hydronium again. So do you think the stoichiometry of this reaction is like, oh, for every one ketone, I need one hydronium? No. Nope. If you have a million of these ketones, you only need a single hydronium. So, for example, if I just have one of these hydroniums, it gets used up and then it gets regenerated and then it gets used up and then it gets regenerated and now it can go and start again. So you only need one hydronium for theoretically infinity ketones, but it just, it would be a lot slower that way, but it can happen. So we say the hydronium reacts in a catalytic amount. And this is like, as I was saying before, one of the things that like organic chemists don't like about this. If this is a problem they don't want to happen, they have to be careful because you don't even need a lot of hydronium. Because it keeps being regenerated in the mechanism. And this concept I'm introducing to you, it's a pretty deep one, but I think you can understand it. How do you feel? Does it make sense that what I'm saying, how it keeps being remade? Okay, good. But if it's a little bit foggy, hang in there. This is kind of a preview. We're gonna be going over this a lot. We'll be going over this again in chapter 17, 18 later. I just wanted to introduce that idea that you could have that happen. Okay, so we got racimization. And then, so originally chemists didn't really know about stereochemistry. And so Louis Pasteur, the Pasteur pipette guy, he was the first to separate enantiomers because they're difficult to separate since they're so similar. And he got lucky. He was able to do a crystallization of tartaric acid, like in tartaric acids in tartar sauce and wine and things like that. So he was able to crystallize tartaric acid, and luckily they formed, the two enantiomers had different crystal structures. One was prisms and one was needles. So like many of you saw needles in lab when we crystallized sulfanilamide. So he was able to take tweezers and just separate the needles from the prisms, and then he saw they rotate plane polarized light differently, and he's like, oh, I made enantiomers. And then he didn't know whether he had like the R or the S, and they hadn't even really come up with R or S nomenclature yet, but he didn't know whether like the two he separated, like this one's wedge or wedge dash, or is it wedge or whatever. But he guessed, he had like a 50-50 guess. And it wasn't until years later, long after his death, that we discovered the technique of Xray crystallography. And his 50-50 guess was right. So he was a smart dude even before well, I guess it's only 50-50 guess, but he was right. And then the cool thing about him being right was that all of our carbohydrates up, like from like the 3-carbon carbohydrates up to the 6-carbon, like glucose and mannose. All their stereochem was based off of the guess. And if the X-ray crystallography said the guess was wrong, then all the textbooks in the world would have to be adjusted, like every enantiomer that people would learn about. Nope, it's the opposite, you know. But the guess was right. So X-ray crystallography, we won't talk much about it, but it's pretty amazing technique. It works by taking a molecule and crystallizing it. The key is you have to have it crystallized. And if you have it crystallized, then you can put it in the X-ray crystallography machine. And what it does is it shoots X-rays at it. And when the X-rays hit the crystal, they bounce off it at a certain angle, depending on the structure of the molecule. And then there's like a detector behind it, the crystal. And so the detector detects where all these X-rays are being deflected to, and then they do all kinds of complicated math to get the actual 3-dimensional structure of a molecule. And it's more complicated. Like I have an analogy. An analogy of this is, say you had a car in a parking lot, and then you threw ping pong balls at it that were covered in paint. When they hit the car, they bounce up the car and they hit a piece of paper, and it makes a spot of paint. You know, you throw more ping pong balls, and you look at all these spots of paper on all these spots on the paper behind the car, and you can do math to figure out the structure of the car. But it's more complicated than that, because when we have crystals of a molecule, there's millions and millions of molecules. So it's like you have a parking lot full of the exact same car, and you're throwing ping pong balls at them all and seeing the diffraction pattern, I think they call it. So, but it's a big one. It helps out a lot. One of the biggest things is, yeah, I'll look it up. Let's go X-ray crystal structure. Say hemoglobin, that's a good one. So you've seen these sort of things before. This is a X-ray crystal structure of hemoglobin. Yeah, this hemoglobin is the protein in our blood that holds iron, that can hold oxygen. So when we're breathing, that oxygen goes into the hemoglobin, grabs onto the iron molecule, which is in the little heme molecules here. So these alpha helixes, these are like they're not the actual structure of the molecule. They're an abbreviated form of it, kind of trying to find one that shows like each atom. Well, here's the hemoglobin. So all this is the protein, and then inside of it, it's got the heme, this circular molecule, and then the iron 3 there is what holds on to the oxygen. And here they're showing this person's being poisoned by cyanide. So the cyanide goes onto the iron instead of oxygen, you die. So that's how, like when you see those movies where the spy behind enemy lines eats a cyanide tablet, cyanide's binding to their heme, and then they can't breathe. Okay, so yeah, here's some more cool ones, huh? So anyways, X-ray crystallography is pretty neat. And one of the things a lot of what X-ray crystallography involves is it's usually some chemist trying to crystallize something, because you can't use X-ray crystallography until you crystallize something. And certain things are just hard to crystallize, like proteins. So a big field is important biological proteins in our body. Chemists around the world are trying to get them to crystallize. And once they're crystallized, then they can put it in the X-ray crystallography machine. So I had a friend in grad school who did that, and he would have like these plates with little wells in them, like 100 wells in this little plate. And he'd have his protein in every well. And then in one well, it would have just water. The next one would have water with like 1 millimolar sodium chloride. The next one's water with 2 millimolar sodium chloride. The next one's like this. You can keep changing sodium chloride, and then you can adjust the pH, and you can add other things to try to get a crystal. And if out of this 100 plate, nothing crystallizes, you just make up another plate and keep trying things. And one day you get lucky and you're like, oh, look at that. Well, 578's got a crystal. Okay, let's try to do that and make a big crystal and get the crystal structure. And once you get the crystal structure, then that can help us understand how that protein works, because you can see like a little pocket where, oh, maybe that's where the glucose sticks, and that's where it gets reactive. Yeah, so Fisher projections. Fisher projections are a way to draw a molecule with many stereo centers quickly. It's actually a very awkward way to draw a molecule, but but it makes it real easy to draw them. I mean, yeah, they're just easy to draw than having to draw, if you have a molecule with multiple stereocenters, having to do all the wedges and dashes. So it's this shorthand notation that I think is pretty good because it gives us another way to get better at visualizing things in 3D. So I'll show you the skills I want you to learn with these Fisher projections. I'm making up a model of one now too to help you visualize it. This is a good one to practice with your model kit as well. I'm going to use white for alcohols, for hydrogen, and I'm going to use a red one here for alcohol. And I made this one blue. This carbon in the middle is red, and the other one's black as it's drawn. Okay, so if I hold this up, does that match up with my drawing for you? The blue carbon has an alcohol wedged out at you, and then a white hydrogen going back. Okay, now it looks good. Okay, cool. So you see how this molecule has 3 stereocenters. It's got a lot going on with it. To draw it as its Newman projection, we're going to twist it around in a really awkward conformation. Watch what I do. I'm going to make all the stereocenters, wedges, and dashes point the same way. These stereocenters are pointing the same direction. And if I hold it like this, you can see it's curving around on itself. It's a real high energy, awkward conformation, but this is how we define Newmans. Not Newmans, these are Fisher projections, not Newman projections. So we have in the Fisher projections, you draw the Fisher projection with the wedged and dashed groups of the stereocenter pointing right at you. So the way we draw this is the way I like to say my analogy is it's like a caterpillar with all the arms coming out to give you a hug, like in a Bug's Life. Like, is it Heinrich? Oh, I'm Heinrich, come have some watermelon with me. He's coming to hug you. So all the wedges and dashes are like arms coming at you for a hug. So let me actually draw this one to show you what I mean. Let me see if I can draw it correctly. Say this one's there, and then I've got a wedged out H, a wedged out alcohol, and then this is going back to the next one. This is my blue one here. My blue, and then the red is next. Which it keeps going around back on itself. So my red one has the OH on the same side, H here, and then finally my black one is going all the way back still. It has the hydrogen on the right and the OH on the left. It's weird, huh? The way it's drawn like that. Does it look like I did it right? If this is blue, I have the alcohol. Do I have the alcohol drawn on the correct side for you? So yeah. So, but we don't draw it like that. That would even be harder than we just drew it. So the Fisher is where Fischer projection. So you draw just a straight line for the groups that are bending back, and then you just draw horizontal lines for the other ones, for the stereocenters. And then we add on our like OH here, OH there, H here, OH there, H, H. So the thing that makes Fisher projections nice is you just draw it up quickly like a straight line into a horizontal line for each stereocenter. So let me point out, make sure you get the idea. I don't know how to spell his name. I-E-N-L-I-C-K. His life. There he is. Is he coming out for a hug? That's kind of like it, right? Heimlich. See his arms, if he was turned a little more sideways, he's reaching out. His arms is like the wedge and dash coming out for a hug. Oh, come give me a hug. That's the way we have to visualize these Fisher projections. And let's look at an example of why these are good. So let's look at carbohydrates. So here are the common sugars. The first one up top here is the glyceraldehyde. It is, it's got one stereocenter in the middle. And the way you'll visualize it is this way. So this equals a carbon with a dashed back aldehyde a wedged out alcohol, because remember his like Heimlich's arms reaching out for a hug, wedged out hydrogen over here, and then a dash back CH2OH. That one we don't have to show as a, it's not a stereocenter, this last alcohol, so. See how that works? And oops, we can assign RNS to this too, because we know like for this stereocenter, the oxygen here would be the first priority. Then this one will be second because it has two oxygens basically. And then this is C. So I have to visualize it because the H is the lowest priority is pointing at me. I want to visualize it like A, B, C. This one's R. R. Okay. And the D nomenclature, it refers to this stereocenter having the alcohol on the right. When the alcohol of this molecule has the alcohol, when the alcohol on this molecule is on the right, it's a dextrorotary molecule, meaning it rotates plane polarized light in the clockwise direction. So D just means for this exact molecule, it rotates light clockwise. But then we have the plus here, it just kind of also says it goes clockwise. It's kind of double nomenclature, it's kind of redundant there for the glyceraldehyde. But now the reason why we do the D thing is when you go from the glyceraldehyde down and you add another carbon. So this had 1, 2, 3 carbons. When you go from 3 to 1, 2, 3, 4, you add another stereocenter right here. And this new stereocenter could have the alcohol on the right or on the left. But you see how we're keeping this one the same? Like this is the same in both of them. We're just adding to it. But the new carbon, new stereocenter we added, that can be R or S. So how are those two molecules related? This D minus threose and D minus threose. Do they have the same molecular formula? Yes. Same connectivity? They're connected the same, actually. They each have a carbonyl of an aldehyde, then a carbon with an oxygen and a hydrogen, carbon with an oxygen and a hydrogen, CH2OH. So they have that same connectivity, but they differ in three-dimensional arrangement. So they are stereoisomers. Are they mirror images? No, they're diastereomers. So they're not mirror images. So these are diastereomers. And then when you add on another stereocenter, you keep, these two stay the same, but you add on that new one. Up top, it can have the alcohol on the left or the right. Okay. And you get all these other ones. You probably heard of some of these. Ribose you've heard of. What's ribose a part of? Yeah, ribonucleic acids, ribose, that's the sugar part of RNA and DNA. And then as you add another stereocenter, you get the allose, altrose, and then glucose you've heard of, that's the common sugar, right? We get energy from. And you maybe have heard of galactose, so mannose maybe, that's in breast milk. Yeah, so these are all like fundamental important molecules, sugars that we need and that nature needs. And they all have this certain stereochemistry where the bottom one, the D-glyceraldehyde stereochem, having the OH on the right, they all have that OH on the right. So you can see in plants and animals, this is made, it's built up from this stereocenter. They all have to have that. And for that reason, they decided to call all of these sugars D sugars, saying they all came from D-glyceraldehyde because they have the OH on the right. So this is from D-glyceraldehyde. So these are all the D sugars. It gets confusing because D means dextrorotary clockwise, but that only applies to the parent, you know, the glyceraldehyde. For example, this is still a D sugar because it's from glyceraldehyde, but it rotates light counterclockwise. See the minus, where this one's D and it's clockwise, D and it's counterclockwise. So that confuses people a lot, but oh well. All right, so the main reason I wanted to show you this slide is just to show you that the Newman projections are helpful, because if I have to draw like Talos here, I got a lot of wedges and dashes to draw. But if I can just draw lines straight across, it's pretty quick and easy. So let's practice. I'll draw some up, and I'll have us first decide like RNS. Yeah, let's do this. Let's work on that first. Let's go. Usually you have the most common Fisher projections to draw are aldehydes, and you abbreviate the aldehyde as CHO. So it looks like this. See how it's got one oxygen, one hydrogen aldehyde. Okay, and then we can throw on our OHs, H's, and we go HH, OH, something like that. And the bottom, usually it's a CH2, OH. Okay, so let's see if I can assign stereochemistry to these. I want you to be able to do this on the exam 3. I'll have you draw some fissures, assign RNS, and then one of the challenging things I'll have you do is I'll have you go from like a fissure like this to a zigzagged type of structure, but I'll help you practice and get good at it. So, but let's work on this first one. Let's number all our carbons. Let's call this carbon 1, 2, 3, 4, 5, 6. Oh, another thing about this, I'll tell you about this. So this guy is formula is C6H2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that right? Am I doing that? No, it's 12. I knew it was 12. I missed the first alcohol. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. O, 1, 2, 3, 4, 5, 6. Yep. C6H12O6. Have you heard of that before? Like in biology, like when they talk about glucose, they give you that formula. Another way to write this formula, it's also equal to C6H2O6. You see how that's the same? So it's like 6 carbons and 6 water molecules worth of atoms. So this is where you get the name carbo from the carbon, right? And then hydrate, because it's got a lot of water. Hydrate like water, like you're dehydrated if you don't have enough water. Okay, so actually, let's see which one this is. I'll go back on my thing. So if I look back, or actually I can cut it out and take it back and see. I just kind of randomly drew this one up. I want to see which one I wound up drawing up. I don't have them all memorized. So I do have a D sugar because I got my lowest alcohol on the right. And then it goes HHOH. Okay. Oh, it's this one. I did galactose, huh? D, because it's made from D-glyceraldehyde. It is dextrorotary. It rotates in the clockwise direction. So it's D. We drew that one up, huh? Galactose. Yep. And then yeah. And oh, but then I think some of you were saying C6H12O6, that's glucose. Glucose has the same formula. So glucose and galactose are same molecular formula, same connectivity, different three-dimensional arrangement. Are they mirror images? No, they're diastereomers. All of these down here are diastereomers because they all have one stereocenter the same and then other ones different. So all of these common sugars are diastereomers. Okay, so let's assign some stereochem to these. So that first one, carbon 2. Let's see what we have here. I'll build it up real quick. I've got a carbon here, an oxygen here, and a hydrogen over here, and a carbon down below. Okay, can I assign any priorities yet? Yes, oxygen's A. What else can I assign? Hydrogen's D. Good job. Okay, and then if I keep going another step, I'll go, this carbon's got 2 oxygens basically because it's an aldehyde and a hydrogen, where the one below, carbon 3 here, has a hydrogen, an oxygen, and another carbon 4. So who's gonna win? The champion of carbon 3 is oxygen. It has to battle the champion of carbon 1, oxygen. They're tied. And now I got to go to the second champion. Carbon 3's second champion is carbon 4, and the second one is oxygen. So that top aldehyde one is going to be B, and this is going to be C. Okay, so are we viewing this? Are we viewing this from the point of view where D is pointing away from us? No, D is coming at us, huh? D is not dashed back. It's not one of those easy ones. And that's pretty much never that way with fissures. So we can do this a number of ways. One way you can do is I like the rose way with this one. I imagine this D priority, the hydrogen. Imagine this is like a stem of a flower and I grab it with my hand and I bring the flower to my face to smell it. And when I do, I see the oxygen, I see the A here, the B, C. And when I'm viewing it that way, it looks like it's S. Okay, that's one way to do it, but you should have more than one way. Another way to do it is the old switcheroo. I keep forgetting to ask Ensley to let me try her pencil caps. I think I'll do better with this. All right, the old switcheroo. So I'm going to switch. What two should I switch here? Because I want to put the D in a position that makes it super easy to view, right? What should I switch D with? Ryan's saying carbon 1. Yeah, actually, I can switch D with either carbon 1 or carbon 3. Doesn't matter which one. Either one will work. I'll switch it with 1. So I'll put I'll put the hydrogen here, and now this is carbon 1 there, and this is carbon 3 here, and this is the oxygen. And now my molecule I've created, it's not the same stereocenter anymore, right? Now it's the enantiomer of the original stereocenter, or it's not the enantiomer unless I switch everything of the whole molecule, but you know what I mean, just that stereocenter. I'll put that in quotes. It's like an enantiomer-like. So this has got the D back, so I can go A, B, C, and this is counterclockwise. This one's S. Oh no, is that S? Is the original one? Let me see. A, B, C. Oh, the original one is R. My flower method didn't work, sorry. Okay, hopefully that didn't throw you off. Did anybody notice I did it wrong with the flower? Yeah, sorry about that. Okay, so so it's a good thing I had two ways to do it. I was able to check. I remember when my wife was in pharmacy school at UC San Francisco, they were doing these Fisher projections because that's an important part of biological systems. And at UC San Francisco, they do a lot of chemistry, actually. They had like chemistry, pharmaceutical chemistry almost every semester. A lot of pharmacy schools don't do that. But one of the things that they did is her teacher, the way they taught it was instead of doing one switch, they did two switches. And if you do two switches, you'd go from R to S back to R. So like if I switched A and B now, so I still wind up with D in the back, it would be R like it should be. So I don't know. If you want to do two switches, you can. Okay, so I got that one. Let me look at carbon 3 here. So on carbon 3, I've got carbon 2 up here, hydrogen here, oxygen there, carbon 4 down below. So I can already start to assign things. I can say oxygen A, H is D, but 2 and 4 are tough. 2 goes to a hydrogen, an oxygen, and a carbon 1, right? 4 goes to the same thing, hydrogen, oxygen, carbon 5. Okay, but then now I got to go to a third step. Carbon 1 has 2 oxygens and a hydrogen. Carbon 5 has a hydrogen, an oxygen, and a carbon. So who wins? The top one or the bottom one? I'll answer your question, Ryan, but top, yes. Answer mine first. All right, so A, B, this is B, and that's C. Okay, so we got our priorities. The 2 oxygens above beat out the 1 oxygen down here. Yeah, my wife works for Kaiser. She's a clinical pharmacist, so she mostly has older patients with heart disease and diabetes, and she's helping them with their meds. They get like blood tests for diabetes, and this would say, okay, lower this med, raise this one. Oh, you're taking this as a side effect of that one. Let's try taking you off of that so you don't have to take that, and that kind of thing. So pain, like medical management is what she does mostly. Cool. All right, so I've got my priorities on this one, carbon 3. I'm going to rewrite it so it makes a little clearer here. So carbon 3, we've got B here, D, A, and C. So D is wedged out at us, huh? And then this is wedged out at us. These are dashed back. So let me see if I grab D like this, it should be ABC. I'm pretty sure it's S. I was wrong last time though, huh? Let me see, S. I'll do the switcheroo. I'll put D down below this time. It doesn't really matter. C here, A here, and B there. Whoops. So now it's going to be A, B, C. That's R. So this guy should be S. Yeah, looks like it's S. So it looks like our molecule, if I'm working down the chain here, the carbon 2 is R. Carbon 3 is S. Carbon 4, I'm going to try to just do it on the structure here. I think it's always gonna win up because of that. We will eventually get to that aldehyde. So we're gonna go A, B, 4. Let me just abbreviate it. It's gonna go A, B, C, D, right? And if I use my flower method, it looks like an S. I do the switcheroo, it would be A, B, C. Yeah, it's an S. Finally, carbon 5. This will be a good one for you to practice later. Draw this molecule up on another piece of paper without the R's and S's and try to figure them out and check your answer. carbon 5 here is going to be, A, D, B, C. Okay. So if I grab onto D, it's R. If I do the switcheroo, A, B, C, yeah, it's R. Okay, so it looks like galactose is RSSR. All right. So Annalise, were you saying maybe I did one wrong? Looks like I can easily mix these up. Or are you just saying how you got it? Okay, cool. Thank you. Please let me know if you think I did it wrong, because I make mistakes constantly. All right, one last thing. I'm going to do this last part really quickly, and then I'll pick it up at this point next lecture. So we're not done with chapter 5 yet, but definitely start homework 5. What I'm going to do is I'm going to try to take this structure, this fissure, F-I-S, fissure projection, and try to make it into a zigzag. Not the cigarette papers, but zigzag line structure. Line bond structure. All right, I'm gonna try it. Yeah, I'm gonna go this way. I'm gonna put my aldehyde on the left. I'm gonna start numbering things. I'm gonna go carbon 1 here, 2, 3, 4, 5, 6. 6 is easy. It's got no stereochem. It's just like that. But then 2 and 3 are a challenge because they have stereochemistry. You have to make sure you do the stereochem correctly. Oh, why am I trying to draw them in yet? I don't even know what they are. Okay, there we go. 1. So 2, 3, 4, 5. They're going to be the challenging ones. So what I do, the way I do this, is I imagine the top part of that molecule with the aldehyde. I see the hydrogen and the alcohol coming right at me. And then my aldehyde's up above, like here. This is the aldehyde, say, right? My text thread's in the way, sorry. So I have on my view, I have the hydrogen here and the alcohol there. And then when I take the molecule and I go like this to put the alcohol over on that side, oh, it's gonna be opposite for you, huh? But I can tell from my view that the alcohol should be wedged out right here. Can you see that? That alcohol should be wedged out? And then the H should be back. Yeah. And then I know for carbon 3, it's going to have to twist around because currently this hydrogen and this alcohol are pointing right at me in the fissure. And this is pointing right at me because it's the Heimlich trying to give me a hug. Oh, give me a hug. But then in the zigzag, it got spun around the other way. So that means the OHs they were on the opposite sides in the fissure, they'll be on the same size here. So I can put my OH on carbon 3 on the wedge. Carbon 4 didn't get turned. It's the same. So the OH should be on the same side as carbon 2's hydrogen. So 4 is back here. But 5, it switched again. So 5 should be, this OH should be on the same side as 4's OH, which is dashed. And then 6, no stereochemistry, so that's easy. Can anyone, I know I did this one fast, we'll work through it slower next time, but I wanted to give you a preview of what we'll be doing to start our next lecture. And can anyone tell me though, a way to check this? What can I do to confirm that this is right? Yes, check the RNS. I can, it's easier to check RNS on this, I think. For this first one, it's ABC, that is clockwise, right? R. Is that what I got for the other one? Carbon 2 should be R, yep. Carbon 3, I've got the A, B, C, it's looking S. And then did I get S on the other one? I did. Carbon 3 was S. Carbon 4, it's looking like A, B, C, but it's from the back, so it's S. Did I get S for carbon 4 before? I did, and I got R for 5. Let's see if I'm getting R again. So on carbon 5, I've got A, B, C. Yep, that's gonna go from the back, so it's R. Yeah, looks like I did it right. So next time we'll do another example of this going from the Newman to the zigzag, and then we're also gonna go zigzag back to Newman. It's a good, more practice with seeing things in 3Ds and rotating things. You'll get good at it. And then after we do that, we're just gonna look at the stereochem of reactions. And the reaction that we spent most of the time with so far has been the radical halogenations of alkanes, right? So if you didn't do well on that one on the exam 1, you should have had it memorized, like where you didn't even have to, you could do it in your head before exam 1. But if some of you didn't do so well on that on the exam, and that really hurt you because that was like over half the test was knowing that mechanism perfectly. So, but it's not too late to memorize it. So memorize it, practice it when you're doing your exam corrections, because we're going to look at that reaction again, but now considering the stereochem. Because in the exam 1, on exam 2, the last exam, we were making stereochemistry, but I was ignoring it and I wasn't showing it. But now we're gonna not ignore it. We know about stereochem. I want you to keep doing well. We did better on exam 2, but the way to keep doing well is go through all these notes and practice doing these problems without looking at the answer. Then make up your own. It's easy to make up your own of these, right? You just draw. Just put an OH over here and an H here and keep the rest the same or something, right? And then do that before Wednesday's lecture. This way, when you come to Wednesday's lecture, you're like ready to go. And the time you spend now learning this is so much easier than trying to learn it in a couple weeks.